exciting short 2-day week. Nice break ahead of you. And I will say that today and tomorrow in honors pre-calc, they're going to be two pretty straightforward days. We're going to start chapter 3. And if you haven't already, go to Google Classroom and open the chapter 3 notes packet. Make sure you find that, take that to Notability, send it to Notability. If you haven't done so already. Chapter 3 covers two new pairs of functions, actually not new because you discussed them last year in Algebra 2. But chapter 3 covers exponents and logs, so logarithmic and exponential functions. Thus far, we have covered in chapter 1 the majority of the basic parent functions. In chapter 2, we looked at the quadratics, we looked at the polynomials, we looked at the rationals. So in chapter 3, we're going to finish the functions, the algebraic functions, and those remaining functions would be the logarithmic and the exponential functions. So the first third of our course with the prerequisite review chapter that we did, and then chapters 1, 2, and 3, that really covers the concepts that you would have discussed last year in Algebra 2. Of course, you've seen that we're going way beyond those functions that you've talked about in Algebra 2. We've dug deeper with the functions that you've covered in Algebra 2 and definitely expanded on those topics. But the first 3 chapters in this class are reviewing and expanding on all of the functions you learned last year in Algebra 2. So that means that after chapter 3, we are going to move into the trig portion of our course. So again, the first 3 chapters are pre-calc, and then the second 3 chapters will be trigonometry. So we will be starting trigonometry on Monday, December 14th. 11, 12, yeah. Monday, December 14th is when we start trigonometry. So today is really the last week of November. Next Monday is November 30th. So next week we will do chapter 3. The following week we'll wrap up chapter 3, and Friday, December 11th, you'll have a test on chapter 3. Chapter 3 is a pretty short chapter. So there's only 5 sections, and they're not nearly as involved as the sections in chapters 1 and 2. So just kind of give yourself a little bit of information there to kind of know where we're going and what kind of comes ahead for us. A little reminder, if you haven't uploaded your chapter 2 notes to Google Classroom, please do so. There's still a handful of you that have not done that. That assignment was posted on Friday for you to upload those notes. It was due yesterday, but please make sure that you are uploading those notes today. It's 10 points for those notes. It's like a little cushion to add to your grade, free 10 points essentially. Your tests were graded and just uploaded this morning into Google Classroom and on PowerSchool. So please look at the comments that I made directly on your test. You should see an edited version when you go to Google Classroom. That edited version is from me. So please make sure that you're looking. Class average on those was about an 85, 86%. So pretty good. I would say in general, that would probably be one of the easiest tests that you would have this year. The amount that it relied on graphing, and you could kind of check a lot of things in your calculator. So kind of think in your mind, like if that's the easiest test that you have this year. So that is what we will be kind of looking and working forward. So they're going to get a little more challenging as we come along. I'd say the mid-chapter test that we took, definitely the more of the level that you'll continue to see. All right, so looking here, we have a couple of problems in your book for homework tonight. It really isn't a lot. 17 to 20 are matching, kind of understanding what in the equation makes the graph perform in a certain way. 37 to 41, you're graphing. I asked you to graph them by hand without a calculator, making a T-chart as we discuss in class. And then 57, 61, 71, 73, 80, those are some application problems. So really, you have about 8 problems to do. 17 to 20 are matching problems. So if you can go into that chapter 3 packet, we're going to talk a little bit about exponential functions today. So the chapter 3 packet, the cover has both exponential and logarithmic functions graphed on them. They are inverse functions. So we talked about inverse functions in chapter 1. So these functions are inverses. They reflect over the line y equals x. That's one of the properties of an inverse function. So two functions are inverses if and only if they're reflections over the line y equals x, reflections of each other. And you can see that we have the log function, which is in red. And then we have the exponential function, which is in blue, and they are perfect reflections of each other. They share that 0.10, which is reflected to the 0.01. So the x-axis or the x-intercept becomes the y-intercept of the inverse. So we'll be looking at those properties in sections 2 and 3 of this chapter. Today we're going to cover exponential functions. I think they're easier to understand than a log function, because a log is like, what the heck is that word log? At least an exponent, we still has an x in it. It's just in the exponential location. So we're going to look at exponential functions today with a base a. And the base is that big number that you see. So if you're looking at these two examples, y equals 2 to the x, the base is the 2. That's that kind of constant number, but it's no longer constant because the variable is now as its exponent. And then in the example right next to it, we have y equals 3 and then to the negative x. So we're going to try and compare what happens if you have a positive coefficient or a positive x versus a negative power of x. So we're going to start by graphing, just to kind of get an idea to how to create these graphs, what the shapes of these graphs look like. As I said, we will be making a t-chart. We're graphing these by hand. So yes, you can use the calculator to kind of check your work, but we will be doing work specifically by hand because we can graph these without the aid of the calculator, which remember is my big goal for you this year, to try and not rely on the calculator, do as much as we can without the calculator to tell us everything to do. So if we graph this, when we're graphing a function, any old function, and where I'm asking you to use a t-chart. Darby, what do we usually pick when we're trying to graph a function and I'm making you use a t-chart? What do we usually pick for numbers in that t-chart?
Normally you pick like -2, -1, 0, 1, and 2 as x values because they're neutral.
And why do we choose those numbers usually?
Because it just is a neutral range of, and normally is easiest to find for all of the functions.
Yeah, excellent. So it gives you a nice range. You have a couple negative, a couple positive, and they're not too large. So if I pick bigger x values, then we probably can't just graph them on our traditional graph that only goes to 10 or -10 on both axes. So we're going to plug these in. Again, no calculator here. So we're trying to do this all mentally to kind of understand what happens with exponents. So I'm going to just zoom in a little bit over here to my t-chart. So Darby gave us a -2 as an exponent. So that means it goes in the exponent location. So my base is a -2. No, I'm sorry, my base is just a 2, but I'm using the exponent of -2. Now think back in your brain to the last 3 chapters, including chapter P. What happens if you have a negative exponent? What does that do to the number? Darby, what happens?
You have to bring it to the denominator to make it a positive exponent.
Yeah. So we need to make it a positive exponent. Again, I don't want you to use a calculator. I don't want to see decimal numbers here because if there's a decimal, then that means you've used a calculator. A negative exponent becomes positive by moving that exponent and the base to the denominator. So this becomes 1 over 2 squared, which is really 1/4. So 2 to the -2 is really the value of 1/4. Notice it's not negative. The negative exponent just moves it to the denominator. So if we look at the second one, we would have 2 to the -1, which is really 1 over 2 to the first, or just 1/2. Again, not a negative number. The negative exponent makes it a fraction. So negative exponents actually make bases into fractions. Then we're plugging in a 0, and we know anything to the 0 power is just 1. Then it becomes a little easier because now we have 2 to the first and we have 2 to the second. So once we're plugging in those positive exponents, it becomes a little easier to work with. So 2 to the first is 2, 2 to the second is 4. So we're going to graph these values, the values that Darby gave us for x corresponding with the value we get for y. So we're going to -2 and only up to a fourth. So that point's going to be pretty close to the x-axis. And then at -1, we're a little higher at a half. And then at 0, we have 1. At 1, we have 2, and then 2 is up to 4. So exponential functions, we say they grow exponentially. They grow quickly. So they increase vertically pretty quickly once you start raising things to a power. Because if I had a 3 for x, 2 cubed is now 8. So I could plot another point up at 8. And I can see that the distance between those 2 points, my 5th and 6th point, is growing. So it's getting further and further apart. And that's what happens with exponential functions. So if we connect these points, they curve vertically. They also skim along the x-axis. So if I continue to have smaller values, like a -3 or a -4 or a -10, it's just going to make my fraction a smaller value. So if you look at this graph, what do you think's going on with the x-axis? What do you think would be happening at that x-axis when y is 0? What feature do you think it looks like is occurring in this graph that we would have just talked about with rational functions?
An asymptote at 0?
Yeah, nice job, Grant. So there is an asymptote here, and I'm going to draw in that asymptote. So there is a horizontal asymptote, and that horizontal asymptote is at y = 0. And that's because a fraction raised to an exponent can never become the value of 0 because there's a base. So that base of 2 will never become the value of 0. It might become 1/2 to the 5th, or 1/2 to the 6th, or 1/2 to the 10th. And that fraction just keeps getting smaller and smaller and smaller, but it'll never be the value of 0. So there is an asymptote at y = 0. So we're going to do the same exact thing for the graph right next to it. This time we have a negative exponent, but we are still going to use the same y values that Darby gave us. So see if you can fill in the t-chart and find the values of y when our function is 3 to the -x. So just be careful. We have 3 to the -x. So Jenny, if we have 3 to the -2,
That
what
would
is
give
the
you
say
that would
again?
give you 9.
Yeah, that's going to give you 9. So it's really 3 squared, which is 9. How about the next one, Jenny?
It would give you 3.
And then when your x is 0, y is?
1.
When x is 1, y is?
1/9.
You're close.
Or 1/3, sorry.
Yeah, that's good. And then 1/9. Nice job. So remember, 3 to the -1 is 1/3 to the first. 3 to the -2 is 1/3 squared, which is how we get 1/9. So a negative exponent makes it a fraction. So if we graph this problem, just like we graphed the previous problem, this time we're going over to -2, up all the way to 9. And then -1, we're down to 3. At 0, we have a point at 1. And then at 1, we're at 1/3 and then 1/9. So I can see that curve happening in the graph. And the distance vertically between each point is getting closer and closer together this time as my x's get larger. So connect those points. And this is going to skim along that x-axis. So just like the one next to it, there is a horizontal asymptote at y=0. So that's going to be a common occurrence with these exponential functions. There's going to be horizontal asymptotes at y=0. And it doesn't matter if the exponent is negative or positive, and that's because of the base. So this number right here, the 2 or the 3, that's called the base. And when that base is raised to an exponent, that number can never be 0. So that kind of takes us down. We're going to see if we can answer the questions down below. These are questions that we've been using and looking at with functions and graphs. So see if you can get the domain, the range, the x and the y-intercept, the horizontal asymptote. Try and answer those questions down below. And you can answer them kind of as both, looking at both functions together and trying to see like the similarities between both of those functions together. So Evan, what would you say the domain of both functions would be?
0 to positive infinity. Or wait, oh, that's the range.
Yeah, okay, I'm gonna put the range down since you gave it to me. What's the domain?
Negative infinity to positive infinity.
Yeah. And he was correct with the range from 0 to positive infinity. So there's that asymptote. They're staying above that asymptote. So the base is a positive base, and all of my numbers are staying remaining above that asymptote. Evan, how about the x-intercept? Does it cross the x-axis?
No.
No. What about a y-intercept?
1.
Yeah, that y-intercept for both of them is at 0, 1. And that's because when you have a number raised to the 0 power, any number to the 0 power is always 1. So you will always have that value because you're raising an exponent. 2 to the 0, 5 to the 0, 15 to the 0, it's always equal to 1. And then one more question for you, Evan. What's the horizontal asymptote here in both of the cases?
Would it just be, I genuinely don't know.
So if you look at the graphs, where is the horizontal asymptote located? The dashed line that we have in both those graphs.
Yeah.
Just at 0. So at y=0 is our horizontal asymptote. So those are the questions that we've been working on with rational functions, and we can still, like any graph, we can analyze. We can give the domain, the range, the intercepts, the asymptotes for any graph. Not all graphs have asymptotes, but exponential functions and rational functions have asymptotes. So there's a couple other questions underneath here that we're going to look at. The first one says increasing or decreasing. Jack, are either of these functions increasing?
The left one is.
Yeah, the one on the left. So the increasing function is 2 to the x. Jack, which one is the decreasing function then?
The other one.
What do you think makes it decrease, Jack? So the other one was 3 to the negative x. What part of the equation do you think makes it decrease, Jack?
The negative sign?
Yeah, the negative. So the negative exponent is what makes it decrease. That's why it's going down, because it's taking really the opposite and it's making do the opposite of the typical values that we're given. So the negative exponent is the part that's making it go down. The number 3, I know that's positive, but that's a 3, a positive 3. It's the exponent that's forcing it to go in the other direction. All right, so we have a couple other questions that we haven't looked at in a while. 1-to-1. So both of these are functions. And when we said if you have a function, we also then kind of talked about them being 1-to-1, which means each y has exactly one x. Remember, a function, each x has exactly one y. That's a function. Now this is 1-to-1. So each y has exactly one x. And that's the horizontal line test. So if it passes the horizontal line test, then we say the function is 1-to-1. And we talk about that because then I can find the inverse of the function. So Caden, would these functions be 1-to-1?
Yes.
Yeah. Caden, I'm going to keep you on. Are they both continuous? So do they start on the left and continue to move forever to the right? Or is there a break in the graph somewhere?
They're continuous.
Excellent. They're both continuous. And then the last part, it says contain what points? Well, it contains, both of them contain that point of 0, 1. And that's going to be consistent or constant for every single one of these functions that we look at. Any questions on those? So you will be asked again to graph 3 of these tonight. Please make a T-chart, just as we did. No, you won't necessarily be asked to analyze them. I think you're just asked to list where the asymptote is. So you'll be asked to kind of determine the asymptote of the graph, but make sure you're doing them by hand without the aid of a calculator. So we're going to look at a couple of properties on the next page. And at the top of the next page, first we're going to just briefly talk about the number e. So besides having a base of an actual number, like the 2 above, so above we had 2 to the x, and we had 3 to the negative x. And this is our base. So a base is a number. But there's also something called the number e, which is called the natural base. And that, whoops, didn't switch my pen, would look like e to the x, where the base is the value, or this number e. Does anybody remember what that actual number is? So it's similar to pi. So pi is 3.14. What is the number e approximately equal to? Okay, good luck. Does anybody remember what that e was from last year? So this would have been chapter 7.
It's 2 point something, right?
It is
I don't
2 point
remember.
something, Jack, yes. 2.718. So the number e, it is a number, just like pi. Pi is a number. The number e is 2.718. Last year, we did a little activity where we were calculating this number e by compounding $1. And we said, what happened after $1 if you have 50% interest? Or what happened after a year? What happened after, if it was compounded after a year, or if it was compounded 12 times a year, if it was compounded, I think we did 365 times a year, like for daily. And then we looked at hourly, and we looked at per minute. And we found that taking $1 and earning interest on it, the more times, eventually we ended up breaking it down just to have this value of 2.718. So that is called the natural base. So instead of having an actual number of 2, 3, 4, 5, it's the value for e, 2.718. And you'll see some equations involving that e as we work through. So we have four functions here that we want to just describe the transformation. So instead of graphing like we did above, we want to describe the transformation. Remember, a transformation can be a shift in a graph or a reflection in a graph. We talked about transformations in chapter 1. So the function that we're dealing with now is an exponential function with a base of a. And the form would be x minus h as an exponent and then plus k. So in chapter 1, we focused on transforming functions with using that h and k and trying to describe how a function moves. How does it shift? Does it reflect? So kind of thinking back to chapter 1, which I know it was a little while ago, we took the chapter 1 test at the very end of September, beginning of October. If you look at part A, we have our function g of x equals 3 to the x plus 1. So it says what kind of transformation would be made to our graph of just y equals 3 to the x, which would be a very similar graph as to y equals 2 to the x. It would just grow a little quicker. But how would this graph shift? So think of that 3 to the x plus 1. I'm going to place that x minus h in there to kind of get you to think. What does that h do to the graph? How does it change the graph? Jeremy, do you know how this graph would shift if there's an x plus 1 as the exponent?
Would it shift to the left one?
Yeah, why does it shift to the left one?
Because I'm not sure why.
That's what you're just feeling like, right?
Yeah.
So
I
we
just know
know that our typical form is x minus, and then if we have a plus 1, that really is going to be a negative 1. X minus a negative 1 is how we get a plus 1. Anytime it's with x, our graph always shifts left or right because the x variable is a variable that moves left or right. So this graph is going to shift left 1 because it's attached, that x plus 1 is kind of attached together. So if it's with x, it's attached with x, x always moves left or right. And again, this is moving left because the formula is x minus. That means our h value that's moving it left is a negative 1. So Cole, kind of looking at number or letter B, we have 3 to the x and then just the minus 2. What do you think that minus 2 does to the graph, Cole?
It moves it down too.
Yeah, so anytime it's outside, that's our k value. Well, k value moves it up or down, and if it's negative, it's going to move down. So when you have a shift in the graph, if it's with x, it goes left or right. If it's next to the base, so 3 to the x minus 2, so it's next to the base, that's our k value, and that's going to shift it up or down. All right, the last two ones are a little different because now we have a negative sign. So let's look at letter D because we have letter D graphed above. Letter D says 3 to the negative x. And if I go to my two pictures and I look at the first example on the left compared to the second example on the right, I know the base isn't exactly the same, but changing the base to a 3 doesn't make much of a difference in the shape of the graph. What do you think would be, how could you describe the change with the graph on the left compared to the graph on the right? Darby, how could you kind of explain that change when you have a negative exponent?
The negative exponent causes it to be decreasing instead
It does
of
cause it to be
increasing.
decreasing. What else does it do besides cause it to be decreasing? What kind of reflection does it look like it?
It takes the y exponents and they start like at a higher number and decrease versus starting at a lower number and increasing.
Yeah, and so that makes it reflect over the y-axis. And as she said, that's because if you're looking at the numbers, like they're switching, my y values are switching. So when you have a positive exponent, the y values start small and they go up. But when I have a negative exponent, the y values start big, so they're doing the opposite and then they're going down. That causes a reflection over the y-axis because the y values are kind of doing the opposite. So a reflection over the y-axis. So that means for part C, when the 3 is negative in front, That's going to reflect over the x-axis. Because now my y values are going to be negative. So what was a positive graph now is going to go down, and it's going to actually go underneath. If I look up here, it's going to go underneath my horizontal asymptote. So if the base is negative, it's making all of my y values negative. It's reflecting over the x-axis. Where for part D, if the exponent is negative, it's reflecting over the x-axis. So kind of looking at the location of that negative. When y is negative, when the whole thing is negative, it reflects over the x. When the exponent is negative, that's when it's reflecting over the y. And that's because we're doing the opposite with x. We're now on that other side of the x-axis. Any questions on that? So the last thing we're going to kind of talk about are a couple of properties. Little review properties of exponents, and I only included a few here. I didn't include all of them. There are actually like 6 or 7 main properties of exponents, but here are 3 of them to kind of review. An exponent has these properties when the base of the exponent is the same. So I'm looking at the a here. If the base is the same, and I'm raising it to a to the x times a to the y. Joe, do you remember what happens if I want to try and combine these together? What do we do with the exponents?
You add them together.
Excellent. Yeah, you add them together. So if I want to combine them together, if the base is the same, I add the exponents together. So if that was a squared times a to the 5th, I would add the exponents and get a to the 7th. So that's a property of exponents. Add them when the base is the same. For part B, if I have a to the x to the y, this is our power to a power property. We multiply those exponents together. So if I had a squared to the 5th, I would have a to the 10th. So that's when I multiply them. So Joe, how about letter C then? If we have a to the x divided by a to the y, what do we do with those?
Subtract them.
Excellent. So maybe I had a to the 5th divided by a squared. Then we would subtract and get a cubed. So those are 3 little properties of exponents. Again, there's more. I just put a couple of here. We'll kind of work more with exponents as we go through the chapter a little bit. So the last main example here, because really the last example just wants you to plug things into the calculator. But our last part here says use the properties of exponents to determine which functions, if any, are the same. So I'm going to start with the one in the middle. Might as well start somewhere. So let's just start with this one in the middle. So our goal is to try and use the exponents to determine if any of these functions would be the same. Right now, they look totally different from each other. But based off of properties of exponents, we might be able to look at these and kind of change the way they're written from the properties to identify which one of the functions could be the similar or the same as one of the other functions that is given. So if we start in the middle at g of x equals 2 to the 2x plus 6. So right now this exponent is considered a condensed exponent. So that 2x plus 6, we added them together. So that's kind of like the first property. Well, what happens instead of if we add it together, what happens if we split it apart? Because our goal is to try and like maybe change the way it's written to see if we can come up with our 2 original or maybe different quantities. So if I have 2 to the 2x plus 6, and I use the property of exponents, that's the product property. But instead of combining them together, we're going to do the opposite and we're going to try and separate them. So if I separate this, I would end up with 2 to the 2x times 2 to the 6th. These are mathematically equivalent statements. All I did was I split it into 2 separate bases. So because of my exponent, because it's being added, I know that's the property, the product property of exponents. So I can separate them and split them apart. So Jenny, if we have 2 to the 6th, do you know what 2 to the 6th is, Jenny?
It's 64.
It is 64. So I can now change that to be the number 64. Now, if we keep using product or properties of exponents, the one on the left here says 2 to the 2x. Well, now if I look at the second property and kind of think of it the same exact way. So the product or the power to a power property says a to the x to the power y is equal to x times y, a to the x times y. So I'm going to work through that and go backwards. So I'm going to take the 2 and then the power of 2, I'm going to attach that just like it's shown, a to the x, so 2 to the 2, and then place the other outside. Well, that other value would just be my variable x. So we're kind of doing the opposite of the power to a power property. Usually we condense it together. Now I'm trying to get you to expand it. So Jenny, if we have 2 squared to the x power, what would that become?
4 to the x.
Yeah, that would become 4 to the x, and then times 64. So my g of x function is really 4, about 64, we'll put that in front, and then 4 to the x. So by using properties, I now see that g of x and h of x are exactly the same. And that's by just kind of taking the property and expanding it or separating these into different pieces. So I want to show you how it works for the other one as well. If I look at h of x, if I kind of just think about the same thing, trying to break this down, if I start with the 64, and now I want you to break it down. So letter G, we kind of broke it apart. I want you to break this down as well. 64 is really 2 to the 6th as an exponent. So breaking it as an exponent. 4 is really 2 squared as an exponent. So those are mathematically equivalent statements. I can just write them in a different form. So I'm writing it as an exponent now. Well, using properties of exponents, 2 squared to the power of x can really be written as 2 to the 2x. And we still have 2 to the 6th. And now, based off of my product property, if my bases are the same, we said we can add the exponents. So the base is the same, so I can take 6 plus 2x. And I can see that this is the same as g of x. The first one does not work because I could write it as 2 squared to the x, but there's no way I can write 12 as a base of 2. It's not 2 squared, it's not 2 cubed, it's not to the 4th, 2 to the 4th. So my two functions that are the same would be our g of x and our h of x, and kind of showing you both ways that the property can work. Does anyone have questions on that? Trying to get you to like apply exponents a little differently, not just evaluate, but getting you to think of how I can take something that's an exponent and break it down, or take a function that doesn't have an exponent and kind of write it in exponential form. So the last problems on here, just plugging these into your calculator, just getting you to remember where the function e would be located in your calculator, or if I have a base of 2, what does that look like to a negative 3.1 or a negative pi? So those are just plugging them into your calculator. So hopefully the homework tonight is pretty short and straightforward. I will say that there are 2 application problems. You will have to look up the formula that you're using for that application problem in the book. So there's a little formula. It's in the section 3.1 of the book. You just have to look up that little formula, or you might remember it from last year, but it would be the compounding interest formula. Tomorrow, we're going to look a little bit with logs, trying to remember how to go from one to the other. Does anybody have questions? All right. Have a fantastic day. I will see you tomorrow. Tomorrow's really the Friday of the week. Have a great day.
Thank you. You
Thank
too.
you. Have a good
Have a
day.
good
See
day.
ya.